Twitter papers. Today we have a Twitter talk.
Not Twitter anymore. Blue Sky.
Yes.
I have to remember to open Blue Sky. Enhorabuena. ¿Te vas a buscar para un café? Okay, let's wait like 30 seconds. Someone's... Okay, so I think we can start already. Welcome everybody. Today we have Emily Hunt. She did her PhD at the Heidelberg University and her degree at the University of Bath. And she finished recently, so she doesn't have like a very long career. Today, she's going to talk us about the how to improve the census of open cluster using Gaia data and machine learning. And all yours, Emily, whenever you want. Thank you.
Great, thanks. Yeah, it's nice to be here virtually and give this talk. So yeah, today I'm going to be chatting all about open clusters. And I get the impression that not everyone here works with Milky Way data and that kind of things. I think it's quite a diverse institute. And so whatever your background, today I'm going to try and convince you that open clusters are important for a lot of different things and that we should care about them. But studying them is quite difficult for a lot of reasons. And there's a lot of different things that I'll get into there and kind of interesting things. So there's hopefully something for everyone, especially with the machine learning aspect, given how common that is. So to start off, I think the nomenclature that star cluster researchers use across astronomy is very, very inconsistent. So I'll start by defining what I mean by an open cluster. So when we talk about open clusters, they're specifically in the Milky Way or maybe the Magellanic Clouds. We don't really tend to look at them in other galaxies. But basically, they're a pretty small star cluster with a mass of typically around 10 to the 3 or so solar masses. And you can even see some of them by eye, like the Pleiades, for instance, is the most famous example here in this picture on the left-hand side. The cool thing about these star clusters, though, is that they're gravitationally bound. And because of that, we can infer that they must have formed at the same time and from the same material. Even when they're, say, 1 billion years old, you can still find small star clusters that, say, maybe a few hundred stars, where you know they formed at the same time and from the same material. And knowing those things is kind of really, really useful for controlling variables when looking at stellar evolution. If you say, look at a really famous diagram like a Hertzsprung-Russell diagram, this is the one for Gaia DR2, for instance, it's really amazing because you see all of these different kinds of phases of stellar evolution, and this is really groundbreaking work and stuff. But the difficulty then is disentangling what's going on here, because you've got O stars at the same time as giant stars. You have this broad main sequence because of chemistry. You've got protos, you've got pre-main sequence stars there. On the other hand, if we look at an open cluster, because all those stars formed at the same time and from the same material, when we look at their photometry, for instance, you can see that all the stars will generally sit on a really, really narrow line, like this case with BH23. The only stars sitting above this line on this diagram of magnitude against color are binary stars, which have misbehaved in many different ways. But for the most part, all the stars will follow a really, really narrow line, which is much, much easier to study than if you're just looking at a Hertzsprung-Russell diagram. You can do things like fit models to this, what we call an isochrone of stars within a cluster. And then you can derive things like age and extinction or distance from just simply from photometry way more easily than you typically can for stars not in a star cluster. And as well as that, when doing chemical studies, you can maybe take chemistry for a handful of stars in that cluster and then relatively safely assume that you know the metallicity now for all the stars in that cluster, which is really, really nice. And it's these kinds of simple properties that make open clusters such a useful tool in so many areas of science. Just to give some examples from the last few years of what people have been doing with open clusters, it's all kinds of things from helping to calibrate the Hubble constant, to studies of our own galaxy, unsurprisingly, even to doing things like testing Newtonian gravity or working with spectra and spectroscopic calibration, or even studying things like how open clusters might affect planet formation. So there's a lot of really, really cool science that people do with open clusters thanks to these kind of simple, cool properties that they have. And as well as that, since 2018, when Gaia Data Release 2 released, it's been a really, really amazing time to do science with open clusters. I don't know how familiar people are with Gaia, but basically the kind of headline news is that it's completely groundbreaking for galactic astronomy. We have about an order of magnitude more astrometric precision, but around 10 to the 4 times as many stars. And this is then so significant because it makes it so much easier to find and work with open clusters in our own galaxy. And so this all kind of paints a quite rosy picture of that we have these really useful star clusters. We have this amazing data that we can work with now called Gaia. And there's so much kind of cool science that people want to do with open clusters. But there is a catch, which is all the different problems with a census of open clusters. There's so much data in Gaia. There's around about 1 billion usable stars at the moment, and there's no perfect algorithm to recover clusters from Gaia. There are so many clusters that are reported before Gaia that we can't find. There are so many clusters that are reported with Gaia that people can't necessarily find, and it's not sure how many of them are real. We don't know how complete our census of clusters is, and the kind of hilarious thing is that we don't even have a good observational definition for an open cluster. I've said that they're these gravitationally bound small clusters, but how do you actually define that in a kind of observational term? And all these 5 different questions will be things that I will get into throughout this talk. Basically, we want to have a good census of open clusters to do all this cool science with them, but there's so many different problems that there still are at the moment. And throughout my PhD, I've been working on trying to fix and improve and contribute to solving some of these issues. So first off, the first thing I worked on was how to detect open clusters. And this is a kind of foray into various different unsupervised machine learning methods. So as I mentioned, open cluster Gaia is really, really amazing for working with open clusters because it has all of this astrometric data, right? You've got the positions of stars, you've got their proper motions and parallaxes, and this is kind of 5 dimensions then of astrometric data for each individual star in the data set. And open clusters stand out really, really clearly within this data. If we look at this plot on the left-hand side here, for instance, this is just a kind of one of my favorite different little segments of the galactic disk in Gaia DR2, and just a plot of the proper motion of, say, maybe about 1 million stars in that region. You can see that most stars have the same kind of bulk motion in the galactic disk here. They all have about the same proper motion. But you can also see these other little clusters sticking out from this bulk motion of stars, and those are open clusters. And actually, when we look at Gaia data now, we see open clusters all over the place in the galactic disk. They stand out really, really clearly, which is great. But the challenge, as I've mentioned, because this is a 1 billion star data set, is to actually automate this process and to go through all of the kind of Gaia data and reliably detect as many clusters as you can. So there's a range of different algorithms to do this that fall under a family of different clustering algorithms. In very simple terms, what a clustering algorithm does is maybe say you have some data, like this example on the left-hand side where you've got clusters in it. You use some algorithm and set some certain parameters in that algorithm, and then it hopefully returns those clusters for you. And in some cases, with some algorithms like dbScan, it will also classify points, in our case, stars that aren't in clusters, into a kind of separate set of things that we don't want to be interested in if we're just looking for clusters. So there's at least a few dozen clustering algorithms out there, but the main problem with applying them on Gaia is that they are mostly just too slow because there are far too many stars in Gaia for most algorithms. So the point of the study, we wanted to try and compare different algorithms. So we settled in the end on just working with the 3 fastest algorithms and the kind of most applicable ones for working with this much data. There's an algorithm called dbScan, which had been used very extensively in the literature at that time. Another one called hdbScan, which hadn't been used as much, but should in theory improve on some things that dbScan does. And then finally, also Gaussian mixture models, which is a much kind of older algorithm, but still has some benefits. And so we still wanted to investigate it. And depending on how you use it, you can use it relatively quickly. It's also related to the k-means algorithm for anyone who's worked on this stuff before, except as a slightly better generalization of that. So it's related to k-means, which is very common in data science as being this really fast, very scalable algorithm. So I'll skip over a lot of the results because there's so many different things I want to talk about in this talk, and I'll just tell you the headline of which algorithm was best. When we looked at everything, actually the one that hadn't been tried that much in the literature, so HDV-scan, seemed to be the best on a lot of different measures. It was the most sensitive, so it was recovering the most open clusters from our test of it on Gaia DR2. It had the best membership lists for the clusters, kind of joint with Gaussian mixture models, which also did really well, better in some respects actually. It was also really easy to use because the parameters are easy to set, but it also has this absolutely massive caveat, which is that it reports a huge number of false positive clusters as well. And so we have this kind of paradigm where we have this really sensitive algorithm that looks really good in a lot of metrics, but it also reports a huge number of false positives depending on how you use it. And this is kind of like a sensitivity accuracy trade-off with this algorithm, and you cannot just trust its results blindly. To look at, again, another piece of example data, this is just 100,000 uniformly distributed points in 5 dimensions. We're just looking at 2 dimensions of it here, with then a 5,000 point Gaussian cluster in the middle. So you can see there's these kind of randomly distributed points around this really, really dense cluster in the middle. This looks kind of analogous to detecting, say, a big open cluster in 5-dimensional Gaia data. But then if we run the HDV-scan algorithm, depending on the parameters that you set, it can return a huge, huge number of false positives. So everything highlighted in the color here is a cluster that the algorithm is reporting. We know this data set should only have 1 cluster, and so it's kind of stupid that HDV-scan itself is reporting so many. The reason for this is the same reason that if you say squint at this image on the left-hand side, you can see that there are regions of any kind of uniformly distributed random set of points that look a bit denser or a bit less dense, just due to random noise. But unfortunately, the HDV-scan picks up all of that random noise. And so a really important part of this work as well was making it possible to use this sensitive algorithm in practice on a big Gaia data that we wanted to investigate. The way I did this was with a post-processing test that basically looks at the density of a cluster and compares that to the stars immediately surrounding it. And again, in very, very quick terms, because I don't want to get bogged down by the maths too much here, because I want to have a kind of broad talk today. Basically, these are the nearest neighbor distances, and this is the probability density of a given point in a cluster having a nearest neighbor distance at some particular distance. In blue here is that for a real kind of very well-behaved cluster, and then in black is for the field surrounding that cluster. You can see in this case that the cluster looks very, very distinct from the field around it, but on the other hand, this cluster that I thought was a false positive looks very, very similar to the field. Then with a little bit of statistics, this gets converted into a signal-to-noise ratio, and if we go back to looking at this example in 2 dimensions again, you can see that only the kind of reliable cluster in the middle has any kind of statistical significance, and everything around it is completely statistically insignificant based on this test. So this is really cool now because we have this sensitive algorithm that we know can find more clusters than any other method, and we also have a way to actually make it usable by getting rid of its, or at least tagging its false positives. And I really want to highlight as well that this is a really important step. Nothing else that I'm going to show you today would be possible without this kind of simple statistical test that post-processes these results. So to start off the study, we investigated all the different algorithms and had this cool result that HDV-scan seems to be more sensitive and that it hasn't been really, and at the time at least, it hadn't really been used very much for open clusters. So it was interesting then to try and detect as much as possible. And for that, we worked with Gaia DR3 to make a single homogeneous catalogue of star clusters. So yeah, basically the aim of this cluster catalogue was to do a big blind search for this big sensitive algorithm that we'd found. And as well as that, by doing a kind of large blind search across all of the Gaia data and to try and find as many clusters as possible, going back to those kind of 5 questions that I highlighted at the start of the talk with these issues in the census, there's quite a few questions and problems that you can answer with doing such a big blind search. Like, if we can't find a cluster in Gaia data at all now after doing this big work with this big sensitive algorithm, then there's a pretty good chance that that cluster isn't real. We can also expect to find more new clusters with this work because we're doing such a kind of big blind search. And then finally, the big advantage as well is that we get to create one single homogeneous catalog where we use the same algorithm on homogeneous data to try and detect things and give people this kind of big end product homogeneous catalog for people to use in the literature for some of these really cool science use cases. So there were also some extra add-ons that I did for this catalog beyond just doing kind of big clustering analysis. The first one of those was to try and really use as many stars as possible. For people who are familiar with Gaia data, you might be familiar with how Gaia isn't so reliable for faint stars. Typically in DR2, people would cut away faint stars entirely, anything fainter than magnitude 18, so from the total about 1.6 billion input sources and Gaia data releases at the moment, you would get around about 285 million reliable stars to look with. Actually, for Gaia Data Release 3, when it came out in the end of 2020 and in early 2021, this really cool paper came out where they used machine learning to classify stars in the Gaia dataset into ones with reliable astrometry and unreliable astrometry. And that didn't have a magnitude cut. And the really cool thing I found was that that massively increased the number of usable stars in Gaia and gave us a lot of new reliable faint sources. To give you an idea of the implications of this, looking at this distant cluster King 9 here in Gaia DR2 data and doing the typical thing of cutting fainter than G18, you can see that you only see the stars beyond the turnoff point for this cluster. But then looking at DR3 and using this cool now way of adding more stars to your data, you can see we get this kind of extra 2 magnitudes of stars. And now for a cluster like King 9, you go from detecting 64 stars for this cluster to nearly 300. So there's a lot of cases where this makes a really big difference, especially when looking at more distant clusters. And this already is another thing where we can say, okay, we expect we'll find a bit more stuff than other works have done because we're trying to use as many stars as possible, thanks to kind of cool kind of things that have developed in DR3 now that the Gaia data is getting a bit more mature. The next thing that's really important with clusters is to check the color magnitude diagram of a cluster and see how, because we expect, right, that one of these star clusters should be a single population of stars where all the stars follow a neat isochrone. In practice, that assumption gets broken for clusters if they're more distant or more difficult to detect, or maybe they're differentially reddened. But basically, I made a neural network that actually was a kind of approximate Bayesian neural network. We won't get into what that means now, but maybe that would be a cool question for the end if someone's curious. But basically, it takes the photometry for a cluster. This gets discretized onto a color magnitude diagram, and then by training this neural network on simulated data of what we expect clusters should look like, it then compares, basically what it's doing is a comparison between, okay, this cluster and then versus how likely is it to be a real single population of stars that formed at the same time and same material. And from that, you then get a probability distribution of how likely that given cluster is to be a real open cluster based on its photometry. In this case, it's a pretty well-behaved cluster other than a few outliers, so the PDF skews really far towards it being a real object, but there's lots more examples of this that I could show you if you're curious of it, say, on a lot of kind of more interesting objects that are somewhere in between. You get a kind of much broader PDF that represents the uncertainty on using photometry with open clusters sometimes. And so it's this really cool base extra add-on that we have with the catalog to be able to classify things into, okay, do we think this is real? Is it maybe not real? Is it maybe somewhere in between? And it would be useful to study in the future and something to follow up on. And the final thing that I did with this was I also modified the network, well, not so much modify the network, but use the kind of existing architecture and training data that I had to also infer some approximate parameters for our clusters. So basically taking a neural network with the same architecture, but instead of telling it to predict how likely a cluster is to be a given single population of stars, instead it's predicting the ages and extinctions of clusters in the catalog based on what it was trained on. This is really nice then as well because we have approximate photometric parameters for all of the clusters in the catalog. They're not super accurate, like if you do isochrone fitting and you have extra metallicity information, you can probably get better parameters, but at least for the whole catalog, we have these approximate homogeneous parameters for every cluster, which is a really, really nice thing. And so after a lot of work to do a lot of clustering in different regions of the disk and try and merge all those results together and a lot of work cross-matching, we arrived at the final catalog. In total, this catalog has 7,167 clusters, 4,100 of which sit into a highly reliable sample of clusters that have a signal to noise ratio of over 5 sigma and also have very kind of clearly good, reliable photometry. And this already is the largest ever, quote marks, deduplicated catalog of clusters. There are cluster catalogs that are larger, but they say maybe look for individual clusters and they don't necessarily give you something where it's guaranteed that there are no duplicate entries in the catalog. So at least this catalog is the largest ever deduplicated and homogeneous catalog of clusters. And we also have these parameters quality criteria for all the clusters in the catalog as well. So as I said, we expected that we would find new clusters with this work, and we found quite a lot. There are around about 739 high reliability new clusters, or around about 2,400 in total. The true number of new clusters will be then somewhere between these two numbers, I expect. For these clusters, we have membership lists down to magnitudes as faint as G20. And also a lot of clusters have tidal tails. I'll get onto that more in a second. I'll talk a bit more about new clusters first. It was really, really surprising how many new clusters we found, and in particular where some of them were. HSC 2384 is by far my favorite example, and I mention it in every single talk. It's been hidden behind a really famous open cluster called IC 2602 for many decades, I assume. I assume people have found it and maybe accidentally cross-matched it against IC 2602. It's only about 550 parsecs away. It's been hidden behind this cluster here in black for all this time. But this is kind of an advantage of doing a blind search because we say, okay, for all of the data, where are all of the clusters? And then we know that they're all kind of separate, distinct objects. And so even within 500 parsecs, we were able to find a pretty big new cluster, which really surprised me. And as I mentioned as well, for many clusters, we detected tidal tails for them. This again was really surprising. I didn't expect that we wouldn't detect just the kind of core of clusters, but also member stars that are being stripped away from the cluster due to the Milky Way's potential. It's something that's been worked with a lot, but it's quite cool that we can find tidal tails for clusters now in a blind search. So we don't even have to try and process each cluster individually, as some other studies typically would do when trying to look for cluster tidal tails. Actually, now we've shown that you can just do a big blind search and recover a lot of additional members for these clusters beyond just the kind of gravitationally bound core of the cluster. So I mentioned as well at the start that a big advantage of doing a blind search is that we get to look for absolutely everything that's there in Gaia data and try and work out how many clusters that were known before Gaia could actually be real based on this. And so around about 50% of clusters from before Gaia are yet to be redetected in Gaia data, including in this work. There's a lot of objects that we couldn't find. And as a part of the paper, I tried to ask why. Is it a limitation of Gaia, or could it be that they're not real? In some cases, it does seem like Gaia limitations are at play, but I would say, based on the work that we've done, that actually a lot of these clusters reported from before Gaia are probably not real. When looking at kind of the largest paper before Gaia called the MWSC catalog from Karchenko et al. 2013, and trying to find which clusters from there we were able to redetect, a lot of people had said that, okay, Gaia is a visual instrument, so it probably can't detect clusters at high extinctions. But actually, when looking at the fraction of clusters that we don't detect as a function of extinction, which is here in blue, and this is against the Karchenko et al. Catalog, you can see that beyond like a magnitude 1 extinction, there's pretty much no change in how many clusters we don't detect, even though I expect that we should be sensitive to clusters down to magnitude 5 of extinction pretty easily. And yet, like, there's so many clusters in this catalog that are at extinctions lower than Mag 5, and there's so many that we don't detect, and it doesn't really seem to be correlated with extinction. So that kind of idea that maybe Gaia is extinction limited doesn't really seem to make sense. And in addition, a reasonable number of the clusters that we aren't able to redetect are within, say, maybe a few kiloparsecs, where again, we expect Gaia should be really sensitive to finding clusters. And so it doesn't really make sense that it would be a limitation of Gaia in this case. And there are maybe at least, I think maybe around about 1,000 clusters that are still missing from the Gaia census of clusters. Ideally, you might investigate all of them individually. That's kind of difficult to do in practice, but we at least have this kind of big homogeneous statistics where we say, okay, there's a lot of clusters that we can't redetect. There doesn't really seem to be a pattern, that maybe they're far away or maybe they're very reddened. So I would posit that probably a lot of these clusters aren't real, and this is something that should be looked into in the future more. In addition as well, a lot of papers have reported new clusters in Gaia data, and we know that we're working with this really sensitive algorithm, and we're using more stars than most of the works have been using to find clusters. And yet again, there's a lot of clusters that we weren't able to redetect. For instance, in the series of papers by He et al., around about half of the clusters we can't detect, and there's no correlation on distance here. In fact, there's kind of the region of distance where we can't redetect the most clusters is where they're closest to the sun, which doesn't make sense because from paper one, we know that HDB scans should actually be more sensitive for nearby clusters. And in addition, there are similar patterns as well for other works. Like in this paper, we only recover about 70% of their clusters. And again, the clusters that we're most likely to not recover are the ones that are nearby to the sun, which doesn't make sense because we should be more sensitive to them than their original work. Depending on your field, you may also be familiar with a series of papers by Kunkel et al. They reported, it was a kind of really big series of papers where they reported these big strings of stars that seemed to be correlated in a lot of groups. I think they had about 8,000 different stellar groups and strings in their paper, but we're only able to recover about 18% of them, even though we're also using the HDB scan algorithm. And despite the fact that we have DR3 data now, which should be better, combined with results by a paper by Zucker et al., who said that most Kunkel clusters are unlikely to be real based on various physical parameters, and also based on this work, it seems that a lot of these clusters aren't actually real. And it kind of shows the value, I guess, of doing this kind of big sort of sensitive work where we do a big blind search and we have all these statistical criteria that go into building the catalog, because we can say with quite a lot of confidence now that a lot of these clusters reported in these really high profile works are actually probably not real, or at least we lend evidence towards that idea, which quite a few papers have commented on so far. But there was one big remaining problem with our catalog, which is that and this again goes back to that kind of fifth issue that I highlighted, if you remember from the back of the talk, that actually it's really difficult to define an open cluster. And when I looked at a lot of in particular, the new clusters that we found, I found that we were finding a lot of new clusters near towards the sun, and a lot of those new clusters seem to have very, very unclumpy distributions. So what do I mean by that? When we see an open cluster, it's generally like a really tight sphere of stars on the sky for the most well-behaved ones. But then if we look at these new clusters like HSC 1131, it looks a bit more like a stellar string. And there's like maybe like a tiny like overdensity of stars in the middle, but it's hard to say. This other one here, HSC 2376, is completely dispersed across the sky. But actually, most of these stars and most of these moving groups and most of these kind of new clusters that look a bit unlike open clusters have reliable photometry. So they look like a single population of stars, and they can be quite a strong overdensity in Gaia data with quite high signal to noise ratios based on the statistical tests that I have. So they look like a real kind of star cluster, but they don't look like an open cluster necessarily. And for the last part of the talk, I'm going to talk about different ways to tell these apart. Actually, the bulk of my PhD was trying to do this and incorporate it into the catalog. It'd be too difficult, so it's now follow-up work that we're doing because it's so difficult to do this in practice. But for the last part of this talk, I'm going to talk about observationally defining open clusters and moving groups, which is based on in-prep work. So previously, a paper by Catalogue and Anders made the kind of previous best approach on how to define an open cluster observationally. Basically, they looked at the big catalog by Catalogue et al. And tried to find additional clusters that weren't possible to find. And they showed that most open clusters have a proper motion dispersion that's compatible with, say, maybe a few kilometers per second at most, and with them, which then kind of implies that it's a gravitationally bound object. And also they generally have radii that are relatively small, which again is compatible with them being gravitationally bound. and they published some constraints to go along with this. But when I applied the constraints to our catalog, actually the vast majority of new clusters, which are these orange squares, pass the constraints. So they're below this dotted black line. There are some objects that really obviously don't pass them, which are low quality new clusters, typically at higher distances, which look a bit more like a stellar stream or moving group. They're quite obvious and easy to get rid of. But there's a huge number of nearby clusters, like the two ones that I showed you on a few slides ago. They both pass these cuts. Even though they look nothing like an open cluster, and when you look at them on sky, they're not clumpy. They don't really look like a star cluster in the gravitationally bound sense that we're familiar with. And so it seems that these upper limit cuts are just too conservative, and that maybe the cuts would need to be defined for each cluster individually. So basically normalizing them based on the mass of each cluster. So say for a larger cluster, you would expect it to maybe have a larger radius and a larger velocity dispersion, and vice versa for a lower mass cluster. So probably one of the most famous pieces of maths that we use in astronomy, the virial theorem, is something that's widely applied to star clusters, at least in theoretical works, and it's something that I dug into for about a year of trying to apply to the star clusters in a sample. Basically, for a star cluster, the kinetic energy of that cluster should go as a half the total mass of the cluster times the velocity dispersion squared. The potential energy is about half the gravitational constant times the mass squared divided by the radius. And you can then put this together and get the what I call or at least what's called the virial ratio, which is the ratio of kinetic energy against potential energy for a given star cluster. And if that cluster is bound, it should be at the order of about a half based on the virial theorem and what we expect for bound objects. And there are these three ingredients that you need to measure, basically: the cluster radius, the cluster velocity dispersion, and the cluster mass. So I tried to do this in practice, and the radii are not too bad. We use the cluster distances that we have in the catalog, do basic trigonometry, and you get a radius that's easy. Cluster masses is not so easy, but it's still doable. I do things like fitting mass functions to the clusters, correct for selection effects, correct for unresolved binaries, and then try and get accurate total cluster masses. But the thing that I always found is that velocity dispersions are so difficult to measure properly. And the virial ratios that I was getting were always far too high for most of the clusters in the sample. They were actually about 10 times the ideal value, which is difficult. We expect that clusters might be a little bit supervirial, depending on how maybe they're dispersing a little bit. Maybe you'd expect a virial ratio of, like, I don't know, 1 to 5 maybe. But most clusters having a virial ratio of this value or higher was pretty crazy and not what we were expecting, and it didn't seem to make any sense at all. There's actually a pattern in the velocity dispersions that I found, and that they always just seem to be too high. Below the masses of, say, the highest mass clusters, pretty much all clusters have a velocity dispersion measured within my method of around about 400 meters per second. The solid red line here is what you would expect a virialized cluster, what velocity dispersion you would expect a virialized cluster to have, given the like typical radius of clusters in the sample. And you can see that the vast majority of clusters are way above these red lines. The velocity dispersions are far too high. You get to, say, a mass of around about 100 solar masses, which is where some of these kind of like smaller, more suspicious objects, they tend to be about 100 solar masses in mass. And you expect them to have a velocity dispersion of about 100 meters per second. They're all like 400 or 500 meters per second, which is way too high and way higher than we would expect for a bound cluster. So something seemed to be going wrong. And after, as is maybe quite common in PhDs, after an eternity of trying things, getting stuck, I found that binary stars were probably to blame in this case, which is a common thing in many parts of astronomy. And I apologize to anyone interested in binary stars in the room. They kind of took a lot of my time in my PhD, and it took a while to solve this. So I am very anti-binary star. I apologize for that in advance. But basically, unresolved binary stars seem to be the reason why the velocity dispersions that I had were too high. I did some simulations of how Gaia does astrometric fitting using this really cool Python module called astromet. which basically simulates how Gaia does this astrometric fitting. So I could say, okay, how much velocity dispersion would we measure for a cluster without any binaries? And then what happens if you put unresolved binary stars into there, where the position of the star within the Gaia data set will wobble, except Gaia fits assume that every star is single at the moment, so they can't really account for that wobble so well. And what I found is that binary stars and the velocity dispersion that you would expect to gain from binary stars, which is this 2D histogram here, looks very, very similar to this contour plot of the distribution of cluster dispersions that we measure. The vast majority of clusters have velocity dispersions that are compatible with being completely due to the binary stars within them. It only really seems to be the highest mass clusters where we can accurately measure a velocity dispersion. And so there are works that have looked at dynamics in clusters. They have, say, maybe been able to really kind of intensively analyze individual clusters. Maybe then you're able to remove binaries based on binary star catalogs. Maybe you're able to do more cutting. But the issue that I found is that binary stars are messing up the measurements. And to get this method to work for our entire catalog of 7,000 clusters was completely impossible. It's impossible to remove binary stars that accurately. And actually for distant clusters, you expect that you're only going to be resolving or seeing maybe the highest mass clusters in or the highest mass stars within that cluster, and so you're only going to be seeing stars that are probably all binaries anyway, so it's pretty impossible to make this measurement accurately. So I dug into the literature a lot and tried to find something that could help solve this problem, and the thing I found was something called the Jacobi radius. Basically getting rid of velocity dispersions entirely and looking for a relationship just between the radius and the mass of a cluster that we would expect for a bound cluster. So it's not necessarily a measure of boundness, it's more a measure of, okay, within some radius, given the potential field of the Milky Way and given the mass of our cluster, do we think it would be instantaneously self-gravitating, or is the potential of the host galaxy, i.e. the Milky Way, stronger where that cluster is and given how big the cluster is? And this is measured with a relatively straightforward equation. Basically, the radius goes as the power of the cluster mass to the third, divided by some constants here, which depend on where the cluster is in the orbit of the cluster and the model of the Milky Way potential that you assume. But at least within the solar neighborhood, that's pretty well resolved. These constants can be determined, I think, relatively accurately. And so we can make a pretty accurate measurement, I hope, of this parameter. And the hypothesis I had basically is that if a cluster doesn't seem to have any radius at which its potential is stronger than that of the Milky Way, then there's a good chance that it's probably not bound. So this is something that has been done a bit before on clusters. My paper that I use as a kind of guideline for this method was Mangas et al. 2020, I think, where they basically looked at some known open clusters and measured their Jacobi radii. Basically, in orange here is the theoretical mass that the cluster would need to have a Jacobi radius of that size, and then in blue is the actual measured mass as a function of radius for a given cluster. Here I'm just doing it for Blanco 1, and you can see that the tidal tails of the cluster, so the stars that we expect to not be bound to the actual cluster itself and that we expect to be pulled away from the cluster core by the Milky Way potential, that's not within the Jacobi radius, but the core of the cluster is. Then this is kind of what we expect, and it seems to work nicely. It's something that's been shown before, and it's really cool. So it's this method basically where we can measure Jacobi radii, comparing the observed mass as a function of radius against the theoretical mass that you would need to have a Jacobi radius of that size. And the really cool thing then was when I tried this on our moving groups, which is not, as far as I'm aware, something that people have tried to look into before. And the really cool thing that I got here is that, say, for these less reliable clusters, like the ones I showed you earlier, HSC 1131 and HSC 2376, they do not seem to have any radius at which they have enough mass to be self-gravitating. But on the other hand, some new clusters that looked maybe a bit more reliable, like this one here, HSC 1185, it's about a kiloparsec away, and it seemed to have a little bit more of a dense core of clusters. It seems to have a Jacobi radius of just a few parsecs, and that contains about 60 solar masses of stellar content. And so there seemed to be a silver bullet where I was actually finally able to distinguish between things that looked a bit more like a moving group and things that looked a bit more like an open cluster. And as well as that, it's also quite clear cut The probability of having a valid Jacobi radius is either basically clusters very obviously have one, or the reliable, well-known open clusters very obviously have a Jacobi radius. And then there's also about 1,000 things that are very obviously moving groups. There's some stuff in the middle, particularly for things that have lower masses. It can be a little bit harder to tell. So I also suggest having a lower mass limit cut of 40 solar masses, because below that I don't expect the method would work so well, and at that point it's also kind of coming into the range of just being a multiple star system and not a star cluster, so it's not really clear how useful it is to have very, very low mass objects. But basically within the classification scheme that I have, we seem to be able to tell much, much better now than ever before between these bound open clusters and unbound moving groups. So one of the first things I did was to look at the distribution of clusters in the catalogue if we now separate them into these two groups, and it looks much, much more like what we would expect. If you remember back a few slides ago, there was this kind of really big overdensity near to the sun, where we seem to have found a lot of new clusters. Actually, we're able to show now that the vast majority of these are moving groups. In fact, 84% of the clusters within 250 parsecs seem to be moving groups in our original published catalogue. And we're now actually able to classify that properly, which is really, really cool. And now it's kind of time to think about the kind of cool things that can come out of this now. We have this kind of big catalog where we've done this big blind search, and we're finally able to tell the difference between open clusters and moving groups better. And there's a lot of cool bits of science that would be possible to do with that I'd like to talk about for the last few minutes of the talk. The first and most obvious thing to me is that we now have a big, big catalog of cluster masses that have been determined for Gaia, while also accounting for things like selection effects and unresolved binaries, at least as best as it can, for so many clusters. And this has then many, many possibilities with such a big catalog of cluster masses. One of the first things that I looked into is whether or not this seems to correlate with the completeness of our catalog. And it actually seems that cluster masses are a really, really strong tracer of how complete a given catalog is. For context here, I think maybe the biggest catalog of cluster masses out at the moment for Gaia data has about 1,000 clusters in it. We have about 7,000 clusters, and it's less biased in how we include clusters in that kind of mass measurement pipeline as well. Every cluster in the catalog has a mass, and so we're able to look into things like the completeness of the census. So looking in certain mass bins, you can see that, say, I don't know, clusters between 50 and 100 solar masses, and the probability that you find them in a given radius as a function of radius, it quite clearly peaks at around about a kiloparsec. For the next mass bin up, it peaks higher and higher and higher. I did a bit more analysis of this and kernel density estimation of our whole sample, and was able to show that there seems to be this kind of clear log linear relationship as a function of mass for the probability that we find a cluster at that given mass, which sort of correlates to a rough completeness estimate. And for that, we're able to show that the catalog is about 100% complete for clusters heavier than 100 solar masses within about a kiloparsec. This is also maybe interesting as well to people who've done star clusters before, because the previous belief from 2013 was that the open cluster census was roughly complete within 1.8 kiloparsecs. Actually, even now working with Gaia DR3 within a kiloparsec, and we know this data should be a lot better than what was available before for looking at clusters within a few kiloparsecs. Actually, now with Gaia and with this kind of mass-derived completeness estimate, it's quite clear that the cluster census is not complete even above a kiloparsec for clusters heavier than 100 solar masses. And that's much lower than the previous belief before Gaia, but at least we're able to get this more accurate belief now. As well as that, there are also interesting things to look into with this. I'm kind of digging into this a little bit more in the final stages of getting ready to publish this. But one of the coolest things I found is that cluster mass seems to correlate quite strongly with how concentrated a cluster is. There are probably a lot of implications here for how theoretical studies could be done. Maybe, say, clusters at higher masses, they start out at a much lower concentration. So this is the median radius of stars in a cluster against the Jacobi radius. You can see its clusters are much more concentrated at higher masses. And as they kind of maybe lose stellar mass, or maybe clusters that form at lower masses and progress along this, they seem to get much, much less centrally concentrated, probably implying that they're losing stars around the outside. But this is the kind of thing that can be compared really nicely to theoretical studies, and it will be exciting to see. And then finally, as well, in this talk, I've mostly focused on showing you results. I haven't talked about methods much, but I really want to talk about selection effects for our masses. I found that a lot of my cluster masses are not very compatible with things that are available in the literature right now, but it's clearly explainable by the fact that selection effects are such a big thing that you have to account for. When I was measuring cluster masses, I tried really, really hard to correct for selection effects. Part of this is only possible because we live in 2023 and Gaia data is much better understood. And there have been some really nice papers, even within just the last year, that give methods and recipes on how to correct for selection effects when working with Gaia. And the kind of thing that I find from this is that after accounting for these selection effects really carefully, like for a cluster like Ruprecht 134, which is very near to the galactic center and is very, very difficult to detect, this is what it looks like if you look in, say, a very deep photometric survey, like decaps around this cluster. There's just stars. You cannot see the cluster. It's just full of stars just everywhere there. When I actually look at the mass function for this cluster now, which is, so the raw mass function we measure is highlighted with these blue points, and then the mass function corrected for binaries and selection effects is highlighted in orange. You can see if you naively look at the stars in this cluster, you might say it has a flat mass function, but then after correcting for selection effects, the slope looks a lot like a Krupa IMF, which is shown here in this with this dashed black line, which is surprising as well because it's quite an old cluster, but it seems that after you account for selection effects nicely, it seems that that is the kind of missing ingredient to have a lot of cluster mass functions look a lot more like a Krupa IMF. I'm working on trying to work out trying to quantify this for the whole sample of clusters. But for the most part, ignoring high mass stars and young clusters, which are these ones here in light blue, which just ignore because that's an issue with my method at the moment. And then also some kind of outlier points, which is due to gaps in photometry and other stuff that we're still looking into. For the most part, all mass functions seem to be roughly compatible with a Krupa IMF. Without doing selection effects, they're all over the place. Without correcting for selection effects, they can be all over the place. But actually, after correcting for them as carefully as I can, it seems that most clusters have mass functions selected with slopes that are roughly compatible with the Krupa IMF, which is a really kind of cool result because there have been recent papers that have suggested that clusters can have really, really steep or shallow mass functions, but actually it all just seems to be a selection effects thing. And so finally as well, because this is something we're planning on publishing really soon, I also want to not oversell this. I think it's really, really cool work, but there are also some limitations and recommendations that I'd have when working with this catalog. We have to make some assumptions to measure Jacobi radii for this many clusters. Like we have to assume that they're on circular orbits, which should be mostly okay. We have to assume that clusters are spherical, which for open clusters is mostly okay, but it could get a bit less accurate for low mass or small number count clusters, which I talked about a little bit earlier with the kind of stuff below 40 solar masses we can't process so well, but it's fine because that's a very, very small number of real open clusters that might be below that mass. But it is something that's very, very usable, and I'm really excited about this for the catalog. It should be the kind of cleanest and best defined catalog, I hope, that anyone's been able to make so far. And a really cool thing about this as well is that I'm interested in this work from a kind of idea of, okay, how in Gaia 4, Gaia 5 will people be finding clusters? And actually, the pipeline to measure cluster masses and cluster Jacobi radii takes a fraction of the time that it took to do the original overall clustering analysis. So this Jacobi radius method should be possible to apply in future works to be able to work out whether or not clusters are gravitationally bound or not, which is really, really cool and really exciting. And this will hopefully get submitted within, well, as soon as possible. We're very, very close to it, definitely by 2024. It should be hopefully fingers crossed accepted and able for people to use as this now kind of big cluster catalog where we have this better definition now between open clusters and moving groups. And so finally, I'll leave you with some key takeaways at the end of this talk. I hope I convinced you at the start that open clusters are really important to astronomy, even if they're really, really far away from what you work on, and that there's a lot of problems that we need to try and fix with the cluster census. And as part of my PhD, we tried to contribute to this in 3 different ways. We tried to look into algorithms to detect them and found that you have to use algorithms quite carefully, but at least HDBScan seems to be really, really sensitive and really effective, at least when you use it with some kind of post-processing technique. From that then, we then did a big blind search and created the largest ever cleaned and unduplicated catalogue of star clusters in the Milky Way so far. And then finally, very, very soon, we're going to publish a result with a new way to define open clusters observationally that will make a big, big difference to the usability of our existing catalog and hopefully to future works, because we have this way now to distinguish between bound clusters and clusters that look much less like they're actually going to be bound observationally, which is really, really nice. And so, yeah, thank you for your time, and that's me done, I guess.
Thank you very much, Emily, for this really nice talk. I think there will be a number of questions, starting with Andres.
Hi, Emily. Thank you so much for a very nice talk. I don't know where I can.
If you want to propose, it's okay. But if you want to ask questions,
Well, I have many questions, but I think I'm gonna restrain myself and just keep it at a high level. So the first one I have is related to the tidal tails that you detect. You mentioned in the conclusions of your work that you assume that the clusters are spherical, but nevertheless you're using HDV scan that, to the best of my knowledge, it doesn't necessarily assume a shape for the cluster. And then also I'm assuming that you're using the 5 solution of Gaia. So this is the 2D positions, 2D proper motions plus parallaxes. So my question was, like, how sure are you that these are really tidal tails? Like, for example, had you done many more verifications, like are these tidal tails compatible with the bulk proper motion of the cluster itself? Like, are they aligned or not? Or
Yeah, so that's a really good question. So to like maybe clear up a bit of misunderstanding first, when I say that we assume clusters are spherical, I just mean the cluster core where we're measuring the Jacobi radius. Even for a very non-spherical overall cluster like Blanco 1, where we clearly have these big tidal tails for it, the actual core of the cluster is spherical, and so the method should still work there. At least maybe a bit of a misnomer in how I explained it. But then how reliable these tidal tails are is a really, really interesting question. So at least for clusters within, let's find some examples, at least for stuff within a kiloparsec, for things like the Blanco ones or your Mamajek pores, these tidal tails seem to be really reliable, and a lot of them align with existing known tidal tails. I still have not actually looked into how many new tidal tails we might have found. I assume that there should be at least a few. But yeah, I would expect that a lot of these seem to be real, but I would urge some caution when looking at more distant clusters. I don't have a good plot here showing it, but another kind of limitation of HDV scan is that it can sometimes assign false members to clusters as a function of their position on the sky. I can't remember the number now. It might be something like Gulliver 16. It's about 6 kiloparsecs away. And the first time I looked at it, I was really shocked because it looked like it had this long tail coming out of it. But actually, all the stars in the tail were completely photometrically incompatible with it. And it seemed like there were false positive members of the cluster. So our tidal tails should be reliable within 1 to 2 kiloparsecs. Further away than that, you probably need to analyze them one by one and make sure that the clustering algorithm has actually worked correctly in those cases. Distant clusters can be harder to detect, so it can get it wrong in those cases. But yeah, at least for the nearby stuff, like, and examples I've shown you today, like Blanco 1, they seem like they're correct. So I hope that answered the question.
yes, but then, so my question would be like, are these tidal tails aligned with the trajectory of the open cluster? Like, what could be produced in these tidal tails? Like, I would expect, like, if they are aligned, then I will argue that they could be caused by the Milky Way potential well, for example, and that they are or something like that.
Yeah, so as far as I know, they are all, at least like reliable ones that people have looked at and detected, they do all seem to be aligned with the ways that the clusters are orbiting. Good papers on that might be like, again, the MindGas 2021, where they looked into it a lot more. For me, at least the tidal tails were like an optional thing that we didn't expect to find, but we did. But yeah, the tidal tails seem to match what we would expect. I think I have a slide somewhere here. No, somewhere at the end. Maybe this is too technical to get into, but yeah, you would expect that I don't know how to show the hidden slide in the slides
It's
properly,
fine, it is.
but yeah, as long as you can see it, basically you expect that clusters should lose stars through their Lagrange points with respect to the Milky Way. So it's actually kind of pointing towards and away from the center of the galaxy is where you would expect to see the tidal tails coming from. But yeah, as far as I know, they're all compatible with that and roughly what you would expect, and theoretical simulations of how tidal tails should be lost. So
Nice. And do I get to
Sure.
like another question? Okay, so the other one is when you were computing the velocity dispersion, I'm assuming that you're using just Gaia data, right? So my question would be like whether you have compared to spectroscopic data from other facilities, whether this could help you to at least make a, refined sample of non-binary stars for which you can derive the velocity dispersion and just to check it whether it's consistent with the expectations.
yeah, so I think there's a lot of ways that work could be improved. Spectra would probably be helpful. I think the issue is trying to get it for such a big sample of clusters, and I'm not convinced that it's the method it's the kind of method we could use to clean all 7,000 clusters in our sample.
Yes.
So I was just using Gaia proper motions for the fact that we can get them for all clusters. But depending on how the radial velocities are measured, say maybe the baseline of how long they're measured for, and I don't know if you're able to say maybe combine spectral data. Like I started this work before Gaia DR3 was released. We were working with EDR3, which didn't have all of these spectra and some slightly better binary star classifications. So it might be possible now to say maybe, I don't know, measure these dynamics for a few hundred or maybe 1,000 clusters in our sample, maybe using RVs and other stuff as well. That would be interesting to dig into, but yeah, at least for our whole sample of clusters, sadly there just aren't enough spectroscopic data available to measure it for all of them.
Yeah, it was definitely not suggested to do it in all the clusters.
Yeah,
just to maybe check on one or two and see if the results are consistent. What would you expect if you were basically removing the binary stars from
Yeah. So I know, I think that at least a few papers have done that already for a few clusters. And I think they find that they're like a little bit super virial, but they're mostly virialized, which is part of why it was frustrating me that I was then trying to do this for a whole sample of clusters, and they were always way more super virial than we expect. But I think those papers where they were able to work with smaller samples of clusters were able to kind of clean their data better than you're ever going to be able to do for so many clusters. But yeah.
Thanks.
Okay, more questions? Alessandro? In the best tradition of good questions, I have a comment and a question. The comment is, I apologize on behalf of the binary stars community. The question is, can you expand a little bit on what is the clustering algorithm saying? This sort of piggybacks on Andres' question. So you feed the clustering algorithm with, I guess, parallaxes, proper motions, positions. You also give it magnitudes and colors.
Yeah, so the clustering is only done on the astrometric data, so it's the positions, proper motions, and parallaxes. So it's always a bit weird with clustering algorithms, and especially with astrometric data, like where we have parallax, which is a bit like a distance, but not quite. And if you try to make it a distance, then things get complicated. And I've tried converting them to distances and trying to do clustering in Cartesian coordinates, but it doesn't work very well as soon as you get a bit too far away. So we actually only give the clustering algorithm the kind of raw astrometry of positions, proper motions, and parallaxes, but all of the dimensions of the data are rescaled to have, I think, 0 median and a unit interquartile range. So basically they all have about the same scale, and they all have a median of 0. So like basically every dimension of the astrometry is weighted equally, is the kind of take home there. And then thankfully with an algorithm like HDBScan, it doesn't really care what data you're giving it. It just looks for clusters and not clusters. And so it doesn't really matter that we're just giving it these kind of dimensions of astrometry that all have different units and different meanings. a cluster is clustered in all of them, and that at least works. It's maybe important to highlight as well that we don't do the clustering in photometric space, partly because a cluster isochrone is more like a long string, so maybe you don't really actually see a cluster in photometry anyway. And then secondly as well, because then you wouldn't be able to use photometry as a kind of independent way to verify the finding. You can have this problem, I think, sometimes, and it's very common in pre-Gaia works where you didn't have astrometry, where maybe you tried to cut the region around potential cluster isochrones really strongly in the photometry. And I think if you do that too much, then you can find clusters where there aren't clusters. So it was quite important to me to not use the photometry actually and just rely on the astrometry. But yeah, basically we feed it the raw astrometry. It's a bit weird, but it works really well. And that's what everyone does in the literature. And I couldn't find anything better when I tried, because if you do any transform to something like distances or real velocities, then you're always kind of having these problems with converting parallaxes to distances, and it spreads the clusters out more and just doesn't work as well. So.
Okay, more questions? I have a question about the evolution of these clusters. Now that you have a good definition and a large catalog, can you say something about the evolution of these systems? Are all of them going to dissolve, or is there a mass above which the core survives?
So that's a really interesting question. There's some of the things that I'm looking into including or maybe doing in future work, but I don't think anything will necessarily get on it that much. I feel like really that's going to be the job of people doing theoretical studies now. Actually, one bugbear that I have is that a lot of n-body work lately, I think, has been focusing more on globular clusters. And we now have so many open clusters to look into. And actually, the processes causing them to dissolve can be very, very different. It's really the Wild West of what causes a cluster to dissolve, when should it dissolve. I remember there are some works, just thinking back to when I wrote my introduction to my thesis and reviewed theory properly, there are some works where like maybe open clusters get dissolved mostly by colliding with molecular clouds, which are then massive enough that as soon as the cluster goes into a molecular cloud or a region with a lot of gas, which happens randomly and stochastically, but as soon as it does that, it then maybe disperses very violently or loses most of its stars suddenly. But then there's also obviously a lot of clusters have tidal tails and they kind of gradually lose stars over time. And I think then it really depends on which n-body model you assume, how often you assume they're hitting giant molecular clouds, how often you do that and this. But there are probably observational constraints on those results and those n-body works that you could get from this work. Like it would be interesting to look at our mass function of clusters at some point and to try and work out, okay, is there maybe some mass at which we're starting to see less and less clusters, which would maybe imply that maybe they're dissolving faster at those masses. Maybe there's some like age mass relationship that we could tease out. Part of the problem with doing that accurately is that you have to correct for completeness accurately. It might be cool to try with just the mass dependent completeness that I have and see if we can get some good results from that. Maybe that would work well enough, and maybe that could then set constraints on future n-body studies. But yeah, it's really the Wild West when it comes to n-body studies of star clusters, I seem, because there are so many different works with so many different conclusions, but we at least now have a lot of observational data that could hopefully be used in the future to constrain that and work out what will happen to open clusters as they evolve a lot further. But...
Okay, thank you. Anyone has some further question? No? We thank again the speaker. Thank you very much.
Thank you, and thank you for the invite as well.
Okay, so wait on. Thank you very much, Emily.
Great, thank you.